So this is a brief summary of the partition functions that we have met so far. So this is a common factor. If you multiply by this factor, then 4 plus 8 is 12, and 16 plus 8 is 24, and you recover the bosonic string. So this lives in 26 dimensions. The rest of the partition functions all concern 10-dimensional string theories. There is a big difference between this first category and the second one. Namely, that this first group of theories are defined with two copies of the superstring on the left and on the right, left and right movers. Whereas the heterotic construction is based on one copy of the superstring on the left with critical dimension 10 and one copy which is mutuated from the bosonic string. I say mutuated from the bosonic string because it's not exactly the bosonic string, because it only concerns the right movers. So there are 26 dimensions to fill, and perhaps the easiest way to understand this matter is that you split the 26 into 10 plus 16, and the 16 extra dimensions are taken care of by 32 fermions, 32 Majorana-Weil fermions that build the gauge group of these theories. Now, all of these models concern closed strings. And the question is, where do open strings fit into this game? Consider that the whole story started with open strings, and by the early 80s, people knew about one model of open strings, which is the type 1 theory. They knew the rules for computing scattering amplitudes, but basically they didn't know where it came from, how it would fit into this picture. And the way it fits into this picture, and in general, even in more complicated examples involving compactifications, has to do with the generalization of the idea of the orbifold construction that we considered last time. Remember that last time we passed from this 2B theory to the 2A theory by projecting out some states and demanding modular invariance, and thereby adding other states that were reinstating this property. Maybe I should also remind you that O8 or O2N in general, in fact, no, for O2N there are some, no, okay, I can say testing. This is theta 0, 0 to the n plus theta 0, 1/2 to the n over 2 eta to the n. And V2n is the same expression with the minus sign. And in fact, S2n, that's why I was reluctant to write it, because there are some i's here. But if n is 8, 16, or 32, then it's simply theta to the 2n, theta to the n 1/2 0 plus or minus theta to the n 1/2 1/2. Let's consider this case because this is what we need. If n is smaller, for instance, it's 1, then or 3, it's an odd number, then you need some i's in this definition, but I will skip on this detail because we don't need it now. So consider it's only like this. So this is certainly true for n equal 4, and n equal 8, and n equal 16, which is the cases that concern us here. Now the question is, how do open strings fit into this game? And let me start, for simplicity, considering the bosonic string. The torus amplitude for the bosonic string is this, integral over the fundamental region, d2 tau over tau 2 squared, 1 over tau 2 to the 12, eta bar to the 24. And let's consider this part here. What is eta bar to the 24? This is 1 over q bar, and then the product of 1 minus q to the n, absolute value raised to the 24, absolute value squared. So let's consider the low-lying states like we did the other day. 1 over q bar, and then we have 1 minus q squared, 1 minus q bar, 1 minus q bar squared, everything of course to the 24, and so on and so forth that I don't write it down. So what are the low-lying states? Clearly the low-lying state altogether is the tachyon, which corresponds to the first term in this in the Taylor expansion around q and q bar equals 0. The next term comes, consider that this expression, if you want to call it, this is sort of an off-shell expression, because it also contains states that don't satisfy level matching. But if I want to look at physical states, I must pick terms with equal powers of q and q bar. So what's the next term? Is that one where I pick one q from here and one q bar from here. And so that term is 24 squared. And then there is this other term of order q bar that I considered last time. And this has to do with the first level of excitation. Actually, we considered it for the open string, but this is sort of the analog of the closed string. But let's consider the first two terms. It's enough. Now, this is one term, and this concerns the tachyon. And these terms here concern what can be built out of these oscillators. Now, you recognize that there are two types of states out of this in this set. There is the symmetric part, and there is the antisymmetric part. The symmetric part is still a reducible representation from this point of view, and it contains the polarization, the polarizations of the say gravity fluctuation and the dilaton, and this one contains the polarizations of the two form. So the polarization of this guy are a symmetric traceless d minus 2 rank tensor, and the scalar is the trace in that expression, and the other one is the antisymmetric combination. The question, can you project this spectrum, retaining only these ones and removing this one? Okay. And indeed you can, because you can essentially decrete that the physical states in your theory are only symmetric under the interchange of left and right. But in order to do that, you must introduce a projection which mixes the left and right modes. This is usually called omega in the literature today. So instead of doing this minus 1 to the f that we did, we have to apply this projection here. So the first part of the story is easy, divide by 2 this amplitude. The second part, we have to compute an amplitude where omega appears in the sum of the states. So how do we do that? Consider intuitively what happens in the torus. The torus is like this, it's a tube, and then everything comes back. And the omega is doing something peculiar, because it's a tube in which you start, and at some point you flip things around. Because the propagation flips in order to identify left and right. Okay? If you flip the closed string all over, then what was a left moving mode becomes a right moving mode, and vice versa. What is the surface that realizes this stuff? Well, the torus, we said this can be understood up to this conformal symmetry that the theory possesses as a rectangle where the opposite sides are identified. If you identify the vertical side, you get a tube. Imagine if you identify this and this, you get a tube. And if you identify the other two sides, you close the tube on itself and you get this surface. If you want to do the other operation, then you are led to the situation like this. The vertical sides are identified, and this is a tube, but in connecting the two, I have to flip it over, which means that the horizontal sides are identified up to the reversal. This surface is a Klein bottle. Sometimes it's depicted like this. but in common life is a self-intersecting surface, but it doesn't matter for the, it's a Klein bottle, but the Klein bottle has a peculiarity, like all these additional surfaces that will serve our purpose. The observation is the following. What are the ordinary Riemann surfaces that enter the construction for the closed string? Well, the first one is a sphere, then you have a torus, then you have a double torus, and you see that this sequence is on the par with the sequence of Feynman diagrams, including no loops, one loop, two loops, and so on and so forth. Okay? And in fact, these are classified by genus, and the Euler character is twice minus twice the number of handles. The number of handles is this intuitive object structure that is present in the diagrams. Now there are more options for two-dimensional surfaces. For instance, the simplest option is that you can put boundaries. If you put boundaries, then, for instance, here, instead of having a sphere, you can have a disk. And here, instead of having a torus, you can have an annulus. And here, for instance, you could have a surface which is like this, for example. Or a surface which is like this. And in general, any surface like this can be decorated by adding an infinite number, any number of boundaries, or holes if you want. So I understand that when you start allowing for this possibility, the whole expansion becomes much more complicated. Because for every surface that you had originally, you could add any number of holes or boundaries, if you prefer, to it. And the complication starts here. However, all these surfaces have the feature of being double covered by special surfaces of the first type. For instance, let's start from the simplest one. This is a disk that conformally can be identified with the upper hemisphere. Add the lower hemisphere, and then you get a sphere. And how do you recover the disk? Identifying pairwise points on the sphere. So if you identify pairwise points, P and P prime on the sphere, then you recover the disk. What do? Any pair of points, you pick only one image. And then there is something interesting that happens. When the point approaches the equatorial plane, it goes on top of its image. So in other words, the equatorial plane is a set of fixed points of this identification. It's a set of points where the original point and the image fall on top of each other. And this continues to be true in this case. For instance, if I draw the annulus like this, I can double cover it like this, and again, I identify pairs of points like this, and then when they approach this boundary, they fall on top of each other. So all these surfaces are doubly covered by the surfaces in the first line, and the only problem is that these surfaces in the first line are generically more rigid because they have to be more symmetrical in order that they can be mirrored into one another. So if you want, the moduli space is restricted, typically to a real slice of the moduli space that you had originally. However, there is a complication that already in this case, there is not only one way to do this identification, but there are actually two ways. And that's the first time in which we meet a new structure, which is called cross-kappa. Take a sphere, doubly cover it, but use an antipodal identification. I don't know if you can see it in the... So if I'm here, say, on this side, I go in the lower hemisphere, but so to speak at opposite latitude. Longitude, sorry, I meant. On the other side of the... Now here there is a big difference, that then the independent points are still in this upper half, but when this point gets here, the other point gets on the opposite end. So there's no boundary, there's no set of fixed points, but this upper hemisphere terminates on a strange circle where opposite points, P and P prime, are identified. And the result is a non-orientable surface. You can play a little bit, move a set of axes in this surface, you will see that they reverse the orientation. Now, this structure here is called the cross cap, or sometimes they call it real projective plane, cross cap. In this context, it's called the cross cap. The reason why I introduced it is because the surface that we stumbled upon is precisely an analog of this surface here, of the annulus, with two cross caps at the ends. So let's try to see it. So the Klein bottle is defined in this fashion. And it can be doubly covered by a torus, because if we take another copy of this rectangle, then the identification flips, no? This is identified with this flipped, and if I start with this flipped, then eventually I identify it correctly. In other words, the double cover, you see, it's a conventional torus, albeit with a rectangular fundamental region. What happens if I do this? Well, this affects any point here. So if I take a point P here, then it will have an image here, P prime. And this is true for any line here. All this line of points will be identified half the way through. Actually, I should have stopped here, because then it comes back there. If you want, I can continue. In fact, when I have a point Q here, the identification goes with the point Q prime here. So you see that line by itself, it flips there. I mean, there are two special lines, if you want. The first one is this line here, which is identified with this line. But since this line is identified with that line, then you find precisely a line in which one point is identified with another point half the way afterwards. So in other words, this line to the left is precisely a cross cap. There is another line like that, which is the line in the middle. Because when I do this reflection, the line in the middle is fixed. And again, any point here is identified half the way through. So you see that I've done the following operation. Let me do it again here. This is the Klein bottle. This is the doubly covering torus of the Klein bottle. And then I found that there is another way of slicing the doubly covering torus, obtaining a surface with the same area. So if you want, as fundamental as the original one, but different from it. And so there are two different ways of exhibiting what's going on here. There is one way of seeing this new surface like this, and another way of seeing this new surface like this. Now this side is identified with this side, but these two ends are two independent cross caps. So if you want, pictorially, this way is identifying the surface like this. Well, I don't know if the picture was not very successful. Let me try the second round. Forget about this. So you have a surface like this, then it goes like this, it flips, and it comes back inside. And the second one is, you see, it's a conventional tube. But at the end of the tube, there are these two structures. Let me do the same thing for the annulus, which is simpler, so that you can appreciate the difference. The annulus, you can picture it like this. It's a conventional tube terminating at two boundaries. Now, if I do what I did here, then I have to take another copy. And this is the doubly covering torus. So if you want, this part here is the one with straight lines. The other one is mirrored with respect to this plane that now is represented like this, hence the reverted arrows. And then altogether, this is a doubly covering torus. It's exactly the same operation that I did there, but in the plane. So again, this surface is is obtained like this. Now you see that there is a difference. That if this quantity here, say, is 1, 0, 1, I tau 2, the doubly covering torus here has a horizontal side which is twice as big, from 0 to 2. The vertical size is I tau 2. So if you want to characterize the doubly covering torus as it should be by the ratio between the position of this point and the size of the horizontal side, this is a doubly covering torus characterized by I tau 2 over 2. For the Klein bottle, on the other hand, you see that this is the Klein bottle originally, and if I get that doubly covering torus, it's the opposite, because this remains 1, this is I tau 2, and this becomes 2 I tau 2. So this is characterized by a doubly covering torus with 2 I tau 2. Now, suppose I add the Klein bottle contribution for the bosonic string. How is the Klein bottle contribution built? Well, basically we use the doubly covering torus, and the torus, remember that I have to do this 1/2 plus 1 plus omega, no? The torus becomes 1/2 integral over the fundamental region d2 tau over tau 2 squared, 1 over eta of tau bar to the 24 times tau square root of tau 2 if you want, times this. And then the omega, so this came, remember, from the trace of q to the L0 dn minus 1, q bar to the n0 n minus 1. Now I want to compute the same thing putting an omega inside. Remember, what was this quantity here, this trace? The trace of q to the n minus 1, q bar to the n minus 1, was the sum on left and right portions and this was factoring, no? It was becoming the sum left q to the n minus 1 left times right q to the n bar minus 1 right, because the two Fock spaces were not talking to each other. Now, if I now do this story with the omega, then if I put an omega inside, then the omega here will reverse left and right. So it will lead you to a sum in which you have left q to the n minus 1, right, left, right, q to the n bar minus 1, left. And now this stuff, only since this operator is diagonal in these states, this has to, you have to identify left and right. And if you identify left and right, then this expression is essentially q bar, and then you can call it left, and here left. So in other words, what you should add, this omega contribution of the Klein bottle term, is naturally built out of purely the left moving portion, because they have to be identified, but depending on QQ bar. So in other words, the integrand there must be the integral only in the tau 2, because I didn't prove it to you, but you can prove that this projection is only compatible with a straight torus or straight torus modulus 1, which is identical. So you have the integral d tau 2 over tau 2 squared from 0 to infinity, and then you get 1 over tau 2 to the 14, to the 12, sorry, eta to the 24 of 2I tau 2, with a half in front. But notice that, first of all, eta to the 4 of 2I tau 2 is precisely QQ bar, because if QQ bar is e to the 2 pi I tau times e to the minus 2 pi I tau bar, then the real part disappears, and then you get e to the minus 4 pi tau 2, which you can write as e to the 2 pi I times 2I tau 2, precisely what you have there. But what I showed you before is that if you look at the Klein bottle and you doubly cover it in a torus, then the modulo of the torus is precisely 2I tau 2. So in other words, the Klein bottle contribution is this. This projection that you are effecting means that the torus becomes this plus this. Now, this is modular invariant by itself, and this is a completely different contribution, but let's manipulate it a little bit. Okay? It's a completely different contribution, but let's manipulate it. And notice also that it's a priori a contribution which has some singular part, because we are not cutting off the origin there. And this will have very important consequences when supersymmetry is broken. It will be a source of back reaction on space-time. But let's proceed in steps. First of all, let me define tau 2 equal t over 2. Because in this way, I work directly in terms of the double covering torus. I call IT this vertical side. Now, if I do this, then you realize that I gain a factor, because I gain a factor 1/2 to the 12 here, another 1/4, and then I gain a factor of 2 here. So, sorry, I got factor 1/2. So altogether, this thing becomes 2 to the 13 over 2, integral from 0 to infinity, dt over t squared, 1 over t to the 14, eta 24 of it. Okay? Because the only change occurs due to the presence of the explicit powers of t, of tau 2 rather, if you want, in the measure and in the denominator. Eta is just rewritten in terms of a new variable. Okay? So now I have this strip here, 0, 1, it. Now let me change coordinates, and I make this guy here 1 and this guy 1 over t. Or if you want, I let t equal 1 over L. Now to compute what happens, we have to do it by the modular transformation. So if I let t equal 1 over L, effectively what I'm doing, I have this doubly covering torus, and I'm counting the shape in terms of this horizontal side L. Because remember, the overall coefficient doesn't matter because the theory is conformal invariant. Before I had 1 t, I rescale, the t becomes 1, the side horizontally becomes 1 over t, I call 1 over t, I call it L, and I get this different representation. If you recall that in this figure, up to a factor of 2, enlarging L means separating the cross caps, this will give you a different dual description of the amplitude. So let's do that. 2 to the 13 over 2. dt over t squared is dl, and I rearrange the endpoints going to infinity. And here you get 1 over L to the 12, eta to the 24 of I over L. Then I use the modular transformation, which tells me that the eta of minus 1 over tau is minus I tau to the 1/2 eta of tau. And I do it for tau, which is purely imaginary, so that this I disappears. Lo and behold, this quantity becomes eta over 24 of IL. So now I have two different representations of the same amplitude, which differ by changes of variable. K, the original one, and this new definition, like this guy, now I will call this different description K tilde. It's the same quantity in terms of different variables. So now I will use this notation, I will call it K tilde. Can you tell me, can you spot the key difference between these two representations? What is the key difference between these two representations? Just compare them. Compare the integrands. What is missing in the second part? In the second formula below, there is something that is present above but is missing there. Sorry? Well, the singularity is more tricky, because there is still. You are also right, but I mean to some extent, because here the singularity is tricky because there is a tachyon. Then there is another singularity because there is another contribution of this stuff. But if you want, the singularity has moved to infinity rather than to the origin. But I want to look at something very simple I'm asking. You see what's missing there? The powers of tau 2. There's no power of L in the other function. Now, if you recall what we did the other time, the powers of tau 2 signaled the momenta flowing through the tube. Remember that they came from the integral of e to the minus tau t m squared, no? When we did this, actually, when we did the trace, the integral over tp squared, and we did the Gaussian integral, we got the power of square root of tau 2 for any momentum flowing, plus another power coming from the measure. Now the powers have disappeared. So it means that this second representation of the amplitude describes a process in which there is no momentum flow. And what is this process which is no momentum flow? Well, this is a loop diagram somehow, right? Because the closed string goes into a loop, flips, but then it comes back to itself. And now here, what we have is essentially, it's a tree diagram. It's a closed string moving from one cross-cap to another with no momentum flow across the cross-caps. The reason why there's no momentum flow is that you are in 10 dimensions, you are respecting all the Lorentz symmetry. The cross-cap is a structure, like a boundary where momentum cannot flow. When you will consider more complicated situations in lower dimensions, then you can have Dirichlet boundary condition, the momentum can flow. Because you will have a rigid object that can take any kick without moving. But here there's nothing. And however, as you noticed, here there is an infrared problem in this stuff. And the reason is the following. That if we expand eta to the 24 of IL, and if we expand it for large L, it's what we did before essentially, then here you will e to the 24 of IL means e to the minus 2 pi L product of 1 minus e to the minus 2 pi NL to the 24. And so if you expand it, this becomes e to the minus 2 pi L plus 24 plus other terms. Sorry, in the numerator, the other way around, rather. E to the 2 pi L plus 24, which comes from the first term in the expansion, in which this exponential, because I mean this stuff I can write it as e to the 2 pi L divided by this product. So expanding power series, this guy, the first term is 1, and then you get plus 24 of this, but if you multiply these guys, you get 1. And then the other guys are all of order e to the minus 2 pi L, or faster. Now you're integrating from 0 to infinity, then you get a very bad infinity from this guy, and this is due to the tachyon. But you also get another infinity from this, and this is due to the dilaton exchange. So in other words, here you are interchanging states in these three-level diagrams, and the states are dealt with exactly like in field theory you saw in previous lectures of Marco. Each of the states comes with a propagator. So in general, if you exchange a state with a propagator 1 over p squared plus m squared between two structures, you will have a reflection coefficient here, a reflection coefficient here, times the propagator. If you work at zero momentum, and we know that there's no momentum flow there, then you will have a reflection coefficient there, 1 over m squared, another reflection coefficient there. If the states have zero mass, then you get a singularity. But it's like a pole that he was finding in those amplitudes, and the residue of the pole has a very precise meaning. The square root of the residue is just, if you want, the coupling between the tube and the cross cap. So if we are careful to regularize things and we pick the coefficient, we identify the pole, the residue of the pole has a very definite physical meaning. And the fact that there is a pole is simply because you exchange a particle zero momentum. The fact that you have an exponentially exploding term is due to the tachyon, but you see, in general, if you have integral e to the minus, say, L m squared dl, you can claim that this integral is 1 over m squared. So in some sense, the tachyon is regulated. It's just that m squared is negative. What you cannot regulate is the massless part. But it doesn't matter, because you know it blows up like a massless propagator at zero momentum, but the residue, if you identify a consistent way of picking the coefficient, and the doubly covering surface gives you the consistent way of doing that, then you have this problem. So summarizing, we can get a theory projecting out this contribution, but we can even do more, because there are other surfaces that we can add upon, and perhaps we can even cancel this, this contribution, this divergent massless part. And what are these other surfaces? Well, one of them is the annulus. So if you want to write the annulus contribution, what is the annulus contribution? Well, from the point of view of the doubly covering surface, is identical. A tilde is some coefficient that I will write in the following form. And this contribution here means boundary, propagator, boundary. So in that thing, I could have called it RC, reflection on a cross cap. And this is this will have the meaning of reflection on a boundary, propagator, reflection on a boundary. What propagates here is precisely the closed string. Now, the fact that I write eta of IL and not eta of 2IL is a choice of representation. I could rescale this quantity, getting a factor of half. But that's the same. I can do it. But it's a closed string spectrum that bounces there. Now, essentially what I'm doing here is discussing the annulus on the doubly covering torus. Now I do L equal 1 over T. And then if I do this transformation, then this expression becomes 2 to the minus 5 n squared over 2 integral from 0 to infinity dt over t squared. I do the modular transformation, I get eta of 1 I over t, and this is t to the 12 eta to the 24 of it. But here I'm still dealing with the doubly covering torus. If I want to work in terms of the proper time of the string flowing onto the annulus, I have to remember that for the annulus the relation is opposite, as I showed you before. So I must define t equal tau 2 over 2. Change variable, then you get this amplitude here. Eventually, the end result, I will call it, sorry, I said 5, but I meant 13 here. You will see that 5 will come up very soon. You can recognize that 13 is half of the dimension, half of the critical dimension, and 5 is half of 10, which is the critical dimension of superstrings, and you know that there is an SO32 group which is special, which will be precisely related to this factor. I was already going forward thinking about what I will tell you shortly. Now, if you do this, this change of variables, you gain a factor 2 to the 13, and you end up with the amplitude that I call A. Now, what did I do with all these changes of variables that go through the doubly covering torus? I gave a prescription for dealing with amplitudes which are individually, if you want, singular. Now, if you want, it's a regularization prescription. I'm comparing different quantities, and in order to compare them consistently, I use the doubly covering torus, which is the common structure, to compare the results. So for the annulus contribution, I have these two. But once in a theory, you have introduced the cross-cap and the boundary as elementary constituents, it's like introducing two couplings in field theory, then the theory is only consistent if you use them both. So in other words, if I wrote an amplitude with boundary, and I wrote an amplitude with cross-cap, then there must be amplitudes of this type. So either I don't introduce this amplitude to begin with, or I don't introduce the other. But if I do introduce both, then there's also an amplitude like this. Notice that I wrote it in two different ways, because these amplitudes are clearly symmetric on the left-right. If you prefer, I can put a factor of half here and not here, but I mean, I want to show you the structure. I need to use all of them, because it's like you have your Lego, your Lego box, and then once you use these tools, by unitarity, you have to use all of them. And it's interesting to see what is this guy. Now, this guy is a counterpart of the annulus, where I identify the strip after flipping the ends. And now this I can draw really. This is a Möbius strip. So let's try to play the game that we were playing before. Let's see what the doubly covering torus is in this case. So I flip around here. Every reflection on a boundary flips the arrows. But I'm not done. I have to continue to do it like this. And the reason is precisely the direction of the arrows. Because this part here can only be identified with this part here. So you see the doubly covering torus is Q in this case. Because you can only identify one line in a doubly covering torus if the arrows are consistent. Up to here they are consistent, and the other part, so if you want, I have two stripped portions which are identified, and along these portions there is consistency in the direction of the arrows. This part is identified with that if you close it. This part is identified with that, but only if you work with a skew torus. So what you have here, you have 0, 1, I tau 2, because I define tau 2 as the time it takes for the open string to flow through the Möbius strip. This guy is 2, and this guy is I tau 2 plus 1. So what's the modulus of the doubly covering torus? It's the ratio between this guy and the horizontal side. So the modulus of doubly covering torus is I tau 2 over 2 plus 1/2. So you have a skew torus. Which means that if you try to write down the Möbius amplitude here, the Möbius amplitude has to be Let's see, where do I do it? No, I don't. I do it not there. This I don't want to erase. I do it on top. If you want to write the Möbius amplitude there, and then it has to be a function not of I tau 2 over 2 like for the annulus, but it has to be a function somehow but there is a better way to proceed, which is essentially unitarity, starting from A tilde and K tilde. Because A tilde is this, if you want. K tilde is this. And so the corresponding vacuum to vacuum amplitude, so cross-cap to boundary amplitude for M tilde, this must be somehow the square root of A tilde K tilde. Sector by sector. Why do I say that? Because this amplitude is boundary, say reflection of the boundary, as we said, the propagator reflection of the boundary. This is a reflection of the cross-cap, propagator reflection of the cross-cap. And what I mean by this expression is that I have propagator, reflection on a boundary, reflection on a cross-cap, and to be really precise, you have a factor of 2 because you lose the symmetry of the diagram. So the overall coefficient is determined by this. To be really precise, it's up to a sign, because I'm taking square roots of real quantities, and so they are defined up to a sign. And the integrand, we know that it has to depend on IL plus 1/2, because IL plus 1/2 is what remains of I tau 2 plus 1/2. So it means that M tilde, if you want, there is a plus or minus, take this coefficient, take the coefficient of K tilde, so the 2 to the 13 cancels, then you get 2 times n over 2, integral from 0 to infinity dl, 1 over eta to the 24 of IL plus 1/2. Now the bosonic string is a bit simple. Do I have to stop? Fine. So let's continue later, because you will see that going back from M tilde to M is more complicated. But once we know this, we will be able to compare the spectra, and once we repeat the argument for the superstrings, you will get to construct all the 10-dimensional orientifolds. Maybe not in the next lecture, and we split it a little, we spread it a little bit over the next one, and you will see all these 10-dimensional examples. So now, before we continue, there is a technical story that is not needed here, but it will be needed shortly, so we better get it straight. What is eta of IL? Which means that it's e to the minus 2 pi over 24 L product 1 minus e to the 2 pi n L. No, because it's 2 pi I tau, and tau is IL. No? This is the... What is eta of IL plus 1/2? It's e to the 2 pi I, let me do it like that, 1/2 plus IL, but divided by 24. Product on n, 1 minus e to the 2 pi I, 1/2 plus IL times n. So let's look at it more closely. I continue to write it here. And now you see that you get this factor in front, which is e to the I pi over 24 e to the minus pi L over 12, sorry, yeah, over 24, yes, product on n. And now this expression is simple because this guy is 1 minus 1 to the n e to the minus 2 pi ln. So in other words, this product is manifestly real. The only difference is that there is this oscillation, which, by the way, corresponds exactly to the effect of flipping the ends of open strings. The same flip property that emerged in other respects when I anticipated something about Champaton factors and the like, as pertains to the fact that the open string has to flip before closing in the Möbius strip. But the problem is that in general, you generate unpleasant complex factors, whereas you are summing real quantities, because you are summing real contribution to the spectrum. So it is convenient, and this will be true in general, because thanks to the GSO prescription, we will always deal, this is true for O, V, S, and C, we'll always deal with combination of states that will give rise to an expression of this type. Q to the H, sum of dn Q to the n. So this will give you the, if you want, the starting mass level, and then the rest will be all integer contributions. That's a GSO, because GSO told us that half integer and integer should never go together. Now suppose that you do the same thing here. You let Q to Q e to the I pi, sorry, Q times e to the I pi, because that's what this 1/2 does for the Möbius strip. And then you get something unpleasant, e to the I pi h times q to the h, sum on n, dn minus q to the n, q to the n. So it is convenient to work with what we call hatted quantities. So to work with the real basis of contribution, if you want. These are the quantities we call hatted. So when we shift by 1/2, we throw away the overall phase, because it's silly to work with something which is complex and have to give it a complex conjugate coefficient to make it real. So we work directly with the real basis. These are called hatted characters. So for instance, the hatted eta over IL plus 1/2 is simply e to the minus pi L over 12 product of 1 minus 1 to the n e to the minus 2 pi ln. So it's real by construction. Okay? So here, although when you raise it to the 24th power, it makes no difference, because this is just an overall sign, it's convenient that I work directly with this quantity, so that when we will go to the superstrings, when you generate complex contribution, you work directly with the real basis, and so this contribution makes sense. Count real contribution to the number of states, if you look at them. With this proviso, we have to learn now how to connect this vacuum channel of the Möbius strip to the direct channel. And in the other cases, we did an S transformation. So in the other cases on top, say for that, we did an S transformation, which is L equal 1 over T. And so let's analyze this connection for the Möbius strip in general, from the direct channel to the transverse channel. Suppose that you start from 1/2 plus I tau 2 over 2, which is what we should end up at the end. Now I tell you that you have to do this series of transformations, which is usually called P. It's not an independent matrix, but it's a very peculiar and important combination of these ones that connects the direct and the transverse channel of the Möbius strip. So suppose you do an S transformation, then this quantity will go into minus 1 over 1/2 plus I tau 2 over 2. Suppose you do t squared. If you do t squared, you add to this quantity 2, put it together, common denominator, and then you will get I tau 2 divided by 1/2 plus I tau 2 over 2. Do an S transformation, which means invert and flip it around. You get minus 1/2 plus I tau 2 over 2 divided by I tau 2. Put the I in the numerator, and you get I over 2 tau 2, and then the other guy becomes minus 1/2. Do another t, which means add 1, and then you get I over 2 tau 2. So the transformation that connects this quantity to that quantity is precisely this P combination. On eta, you can prove that this P combination, or in eta hat, does exactly the same. But in order to apply it, the argument must contain a half here. So I must rescale the measure, losing a factor of a half. So I must define 2L equal, say, t. And then I have dt 1 over eta to the 24 I t over 2 plus 1/2. Then I define t equal 1 over tau 2. So this quantity becomes plus or minus n over 2 integral d tau 2 over tau 2 squared. And then this quantity is eta to the 24 I over 2 tau 2 plus 1/2. Then I use the fact that eta, or eta hat is the same, of I over 2 tau 2 plus 1/2 is tau 2 to the 1/2 eta hat of I tau 2 over 2 plus 1/2, which is what I anticipated. So what do I get at the end of the day? I write it here in this intermediate line. So this is the vacuum description of the Möbius strip, and the standard direct channel one, as it's called, at the end of the day becomes this. So let's see what the spectrum of the open string is. We have to consider for the open string the contribution of this and the contribution of this. So let me do it on top. So what did we achieve by these steps? Let me write the two expressions here. There's no issue of level matching here, so we can simply count the contributions level by level. So let's look at the low-lying states. So all I need to do is compare the contribution of this guy and this guy. The rest is a common part of the measure, but I have to take into account the factors in front, which are multiplicities of states. Okay? So the annulus gives you n squared over 2, and then you get 1 over square root of 2, square root of q, because if this thing were tau 2, I tau 2, or rather, let me do it more explicitly. N squared over 2, and then eta to the 24 of I tau 2 over 2 means square root of q, product on n, 1 minus square root of q to the n. The Möbius strip gives you plus or minus n over 2, 1 over square root of q. Remember that I'm working with eta hat, so there's no issue of phases in front. Product of 1 minus 1 to the n, square root of q to the n. So let's expand the first two levels. Then the rest will continue. You get 1 over square root of q, and in this case you get plus 24. And in this case, this is the important difference. You see there is plus or minus n over 2 in front. It starts again like 1 over square root of q, but the first oscillator is flipped. So instead of having 1 minus square root of q here, you get 1 plus square root of q. So at the next stage, you get minus 24, plus all the... And you get these flips for the oscillators of level n. So how many states do I get at the lowest level? Well, at the lowest level, I get n plus or minus over 2 states. So these are the tachyons. How many vectors do I get? I get n minus or plus over 2 vectors, because the 24 is just a number of polarizations of the vectors. Now, for a given value of n, if you pick the upper sign, it means that the polarizations, the Champaton matrices, if you want, for the vectors are antisymmetric. And if you pick the plus sign, the lower sign, it means they are symmetric. If they are antisymmetric, the gauge group is an orthogonal gauge group. If they are symmetric, it's a symplectic gauge group. So you are describing a theory where the vectors are valued in the adjoint of an orthogonal group, SON, if you pick the upper sign, or of a symplectic group if you pick the lower sign. What we haven't described, what we haven't selected is the value of n. When we move to the superstrings, you will see that the selection of the value of n is compelled by the cancellation of anomalies. But here there is still nonetheless a special value of n. And the special value of n we can identify going back to the vacuum channel. Because if I look at the contributions in the vacuum channel, all of them, k tilde, a tilde, and m tilde, I can look at the contribution of the unregulated massless exchange. Remember that in string theory, what you really have under control are on-shell amplitudes. It's amazing that we are giving 2 courses in parallel that have looking at very different things, but with a very similar philosophy in many respects. Here, the only thing that you have under control are on-shell amplitudes. And the only amplitude that goes on shell at 0 momentum is the massless amplitude. That's the only one from which you can extract really this reflection coefficient in a sensible way. Now, k tilde was written somewhere there. Where was it written? Disappeared, but I can reinstate. Maybe it's below, but I can write it here. So what is the contribution of k tilde, of the integrand of k tilde to the massless level? It's 2 to the 13 over 2, which is in front, and then I have to perform the same expression, the same operation that I performed here, barring the replacement of square root of q with q. But anyway, this contribution is 24. What is the contribution of a tilde? Same thing, because a tilde has the same, you can call it like that. So a tilde gives you 2 to the 13, sorry, not 2 to the 13, to the minus 13 over 2, n squared, times again 24. And the Möbius strip, which is this quantity, remember that there is flip of sign here, because I'm looking at the first excited level, so you have minus or plus 2 times n over 2 times 24. Is there a choice of n by which these contributions add up to 0? Yes, there is a unique one, because you see this, you get a quadratic equation of n for n, but it has 2 coincident roots. And the reason why it has 2 coincident roots is that you are identifying the square of a combination. By unitarity, we fix the coefficient of the Möbius amplitude, vacuum to vacuum, say, representation of the Möbius amplitude as the geometric mean of the other 2 up to a factor of 2. And this implies that this polynomial that you get here in n has 2 identical roots. So if you write it in like this, you get a 2 to the 13 over 2 times 24, and then you get 1 plus n over 2 to the 13 squared from the annulus. And then you get minus or plus 2n over 2 to the 13. And so you see that there is only one possibility to cancel it with a positive n, upper sign, and n equal to the 13. And this is something that was discovered in the mid-80s, that there was this special theory of open strings where this contribution was canceling. What is this contribution? Is the total coupling of the dilaton, which is the only massless mode that can couple in a Lorentz invariant way in the critical dimension to boundaries or cross-cap. So if you want, you can write this condition symbolically like this, in the sense that the total coupling of the dilaton to the cross-cap and the boundary vanishes for this theory in the critical dimension. We will come back to the meaning of what happens if this thing is not the case, because at some point we will find that when supersymmetry is broken, this type of contribution cannot be cancelled in the superstrings. Maybe I can anticipate what it means. It means that the effective action will involve an additional term, but we have to talk about the low-energy effective field theory first, but let me write it. And we'll introduce an additional term that will be of this form, dx, where d could be 26 or 10, square root of minus g, e to the minus phi. Where is the dilaton? This term I will call it a dilaton tadpole potential. So in this case, there is a special bosonic open string that doesn't have a dilaton tadpole potential. Now, the most interesting part of this story is that it revealed the meaning of SO32 in the 10-dimensional Green-Schwarz construction. Because from the heterotic point of view, you've seen that 32 means 2 times 16, or 32 real fermions, if you prefer. It has to do with the unbalance between the critical dimension of the left superstring part and the right bosonic part. In this case, 2 to the 13 is obviously 2 to the dimension of space-time, of the critical space-time dimension divided by 2, 2 to the 26 over 2. And if you rephrase the story in 10 dimensions that I will do shortly, 2 to the d over 2 will become exactly the 32 of the superstring. So it tells you that the gauge groups that have to do with this open strings are related exponentially to the dimension of space-time. So now let's go to the superstring. Let's repeat the exercise. So we will rediscover by this systematics what is the logic behind the SO32 type 1 superstring. First of all, what is the parent of the SO32 type 1 superstring? What's the analog of the bosonic string that generates the type 1 superstring out of this? What is it? Remember that you have to mix left and right modes. There's only one option, if you see that. So these guys are out of the way because left and right modes have nothing to do with each other. So you have to pick here. Out of this and this, which one is it? The mother or father of the type 1 superstring. Which one? Huh? 2b. Because this theory, although it's chiral in space-time, is completely symmetric from the two-dimensional point of view. So if I start from the 2b, I can repeat almost verbatim what I did here. And so the 2b and the type 1 theory will be connected, which is one of the sides of this famous hexagon in 10 dimensions, which you will learn about completely. This is just one of the 6 sides. So the torus amplitude, proceeding like before, is this one. So the torus amplitude should go to 1/2 of itself. And the Klein-Bottle amplitude, in this case, will be simply 1/2 integral from 0 to infinity d tau 2 over tau 2 squared. The denominator, there is no question. In the numerator, you can start wondering about signs. No, the logical thing to do is this one. And the reason why there are many reasons why it's logical. The first reason is that this is the Jacobi identity that tells you that V8 numerical is equal to S8. So if you add this contribution, you're not back reacting on space-time. But there are other reasons for that. The second reason is that I told you that the characters, the objects that you are allowed to use independently in 10 dimensions compatible with GSO are really O, V, minus S, and minus C. Remember, that's what I told you, no? Because the characters that behave correctly in 10 dimensions have an extra minus sign for these Ramond characters here, for the Ramond contributions. Effectively, what this thing is doing is symmetrizing the Nevers-Schwarz sector, anti-symmetrizing the Ramond sector, and the factor of 1/2 symmetrizes the Nevers-Schwarz-Ramond sector. So in other words, this factor of, you start from a theory which at the massless level contains the graviton, dilaton, antisymmetric tensor from the Nevers-Schwarz, then contains another axion and a self-dual for form from the Ramond, and from the Ramond-Nevers-Schwarz and Nevers-Schwarz-Ramond contains a first gravitino, a right spinor, a second gravitino, a second right spinor. The 1/2 here that affects the off-diagonal terms tells you that you only get one combination of this thing. So you halve the number of fermions. Because the number of fermions appear off-diagonally. So this guy here only, you have to imagine that this guy here is the same thing as, you have to read it somehow as a VV bar, and this guy as an SS bar. It's like for the bosonic string. Remember, it's a function of Q squared. So it was giving 24 times 25 over 2 states. No? So it's symmetrizing those things. Now, this guy is symmetrizing the Nevers-Schwarz states, and it's anti-symmetrizing the Ramond states. Shortly, I will play it with signs, and I'll show you that you have no other way to do it consistently. Now, if you symmetrize the Nevers-Schwarz states, you throw away this guy. If you anti-symmetrize the, sorry, I forgot here an important state, is a B prime, you know. So if you anti-symmetrize the Ramond states, you're left only with that. So you see that at the end of the day, the theory contains a metric, a dilaton, and an antisymmetric tensor, but the antisymmetric tensor comes from the Ramond sector in this case. And then it contains a gravitino and a spinor. So in other words, the closed part of the theory is type 1, 0 supergravity, which, as I told you before, is a sick theory, it's an anomalous theory. So if this construction is consistent, it will tell you that you cannot stop now. So first of all, let's see that we didn't have any other choice. So suppose you want to say that, okay, I want to put here V plus S. Yes?
Can you say again why the B field comes from the Ramond this time?
Say it again?
Can you say again why the B field comes from the Ramond this time?
Because the Nevers-Schwarz is manifested, it's eliminated, no? Because I'm symmetrizing it, okay? The other one, I have to play with gamma matrices and show you, but the point is that in the Ramond part, phi prime and the self-dual for form are symmetric, and the B prime nu comes in the antisymmetric part. So altogether you're left with those states. Now, suppose that I say I don't want to project like this. I want to project the other way. Let's see what happens. Remember that if I perform the steps that I did before, so let's perform first the steps that I did before. I let tau 2 equal t over 2, and then this expression becomes 2 to the 5 over 2 integral from 0 to infinity dt over t squared v8 minus s8, this time of it, divided by t to the fourth eta to the 8th of it. Now I go to the transverse channel, I put t equal 1 over L. And if I do this step, eventually I'm looking at the amplitude for the closed string, which is given there, to propagate between two crosscups. Now, what states can propagate between two crosscups in 10 dimensions? Well, the states of the Navier-Schwarz, and the state of the Ramond-Ramond. Because they have to reflect in a Lorentz invariant way, and the only way to do it is that the left and the right part are the same. We are talking about real representations. The singlet is only in the product itself. What happens if I do the modular transformation? Well, if I do the modular transformation, I get this amplitude which I call k tilde. Now you see the 32 emerging already. So dt over t squared becomes dl. The denominator I know that becomes eta to the 8 of il. And then, as I told you, v8 minus s8, if I do an s transformation, goes into itself. So v8 minus s8 becomes v8 minus s8 of il. Because v8 minus s8 of I over t becomes, or I over L becomes v8 minus s8 of il. I gave you this S matrix the other time that does it. Suppose I say, no, I want to start and do v8 plus s8. But if I do this thing, if I do a modular transformation, this becomes O8 minus C8. It's inconsistent because there's no tachyon, there's no O bar in the superstring that can flow there. There's no CC bar. So you have no other way to do it. Okay? Suppose you want to do something else. Okay, yeah, I'm abiding to use this combination, but I want to put a minus sign in front. That would be dramatic because you would project out the graviton. Okay? What do you violate? You violate unitarity if you want here, because this quantity is propagator, reflection coefficient, refraction coefficient. Positivity tells you that you cannot change the sign of that term. So you have no other way. V8 minus S8 is the only projection. But we have two problems at the massless level. There is a massless contribution from here, and this is akin to what we did for the bosonic string. So there would be a dilaton tadpole by that. But what is worse, there is a massless contribution from this Ramond-Ramond sector. And this translates directly into a gauge and gravitational anomaly. Or to be more precise, if you know a little bit what I'm talking about, what I will try to tell you the story a little bit in the next lectures. The anomalies in 10 dimensions are defined in terms of symmetric polynomials in 12 dimensions. And there is an irreducible symmetric polynomial, a trace which doesn't factor. And this term is in one-to-one correspondence with the coefficient of this term here. If this term is not cancelled somehow, then you have a non-reducible trace. The non-reducible trace is an anomaly. You can't do anything about that. If the non-reducible trace cancels, the reducible ones, the ones that factor, can be cancelled by the Green-Schwarz mechanism. But this term we need to get rid of. How do we get rid of this term? Well, we define an annulus amplitude, which I normalize it like this. It's just a definition of n if you want. I define an annulus amplitude like this. This amplitude and that amplitude imply a Möbius amplitude, which is plus or minus. Actually, there are two plus or minus because there are two sectors here. But the overall coefficient should be the geometric mean times 2. So it should be 2n over 2, integral from 0 to infinity. And then a priori there are two signs here. Hatted quantities, so that they are real. So effectively, once you are introducing these things, you are introducing an open spectrum. So what we must do now is go to the direct channel for the open part and read the open spectrum that we have introduced. How do we do that? Changing variable and performing modular transformations. Let me do it here. Very similar to what we did for the bosonic string. So K we know already. I want to get A. So to get A, I let L equal 1 over T. You know that V8 minus S8 of I over T becomes V8 minus S8 of IT. The measure dl and the eta reproduce the powers of T. So I get 2 to the minus 5 n squared over 2 integral from 0 to infinity dt over t squared. dl became dt over t squared. V8 minus S8 became V8 minus S8 of IT. And the guy on the denominator became t to the fourth eta to the 8 of IT. Then I want to work in terms of the proper time of the open string, because remember that the spectra of closed and open strings are off by a factor of 4. We did it from the beginning. And so this quantity finally defines the direct channel amnus amplitude, which is n squared over 2. You see, if you let t goes to tau 2 over 2, you get again a factor of 2 to the 5. So that's the annulus. The Möbius. Remember, for the Möbius, we have to start from IL over 2 over 2 to perform a P transformation. So if we have to define L equal T over 2, then I lose a factor of 2. I get a factor of half from the measure. So in M tilde, I start from n over 2 integral from 0 to infinity dt, and then I have say this plus or minus V8 at minus plus or minus prime S8 at, well, I could have put not this, there's a sign which is, I mean, it's too much, but it's nothing wrong, but it's a bit redundant. Now, I perform the modular transformation because I define t equal 1 over tau 2. And then what happens is the following. Well, dt clearly goes into d tau 2 over tau 2 squared. V8 minus S8, you can show that by the P transformation goes into itself. And then this guy becomes tau 2 to the fourth, eta to the 8 of I tau 2 over 2 plus 1 half. And the numerator, of course, is again a function of I tau 2 over 2 plus 1 half, which you know it means that you get alternating contributions for the various mass levels. But now it's easier to read because this spectrum starts from the massless level. So what the sign here is the sign in the spectrum. Remember, for the tachyon, the sign was manifest for the tachyon, but for the other one we have to flip because it was the first excited state. Here the spectrum starts at the massless level. So this choice means, with these signs, that you get n plus or minus 1 over 2 vectors, this contribution plus this contribution, and then you get n plus or minus prime plus 1 over 2 spinors. Because in the open string, there's no S bar. I mean, here you read the spectrum. The spectrum starts at the massless level, so everything is. So you see that if you if you take plus or minus equal plus or minus prime, then the number of vectors is equal to the number of spinors. Or if you prefer, if these two choices of sign, still ambiguous, are identical, this stuff can be written as V8 minus S8. And again, remembering the Jacobi identity, if you compute numerically the contribution to the vacuum energy, you have to put the numerical values of V8 minus S8. This is 0, this is 0, the Klein bottle is 0. This is 0, the theory doesn't back react on space-time. So the space-time, you start with flat space, you end up with flat space, the spectrum that you read is precisely the spectrum of the low energy excitation. It's not corrected. Now the question is the tadpole. But in principle, you would have another choice of disaligning these two sectors. The important thing is that the S8 coefficient in the transverse channel should be cancelled, because that has to do with the anomalies. We have no choice. So let's track that coefficient. First, let's do it in this case. Actually, this case is what the only thing I will deal with today. So what are these coefficients? K tilde, where did we write it? Here. Let's look at the coefficient of S8. K tilde gives you 2 to the 5 of minus S8, rather, if you want. 2 to the 5 over 2. A tilde, it's written there. It's written, where is it? Where is A tilde? It's written there. A tilde, the coefficient is 2 to the minus 5 m squared over 2. And M tilde, I'm looking at the case in which the signs are correlated, but then it's plus or minus 2 over 2 times n. So n is a positive number, is the multiplicity, my convention is a positive number. You could take it negative and start the discussion again, but my convention is a positive number, and you want to solve this quadratic equation with the positive value of n. So there's only one choice, minus sign here, and n equals 32. So if n is equal to 32 and you choose the minus sign there, you have cancelled the Ramond-Ramond tadpole, as it's called, and this condition translates immediately into the cancellation of gauge and gravitational anomalies. Of course, it requires another lecture to understand that, or more, but I mean, this is, you can take it for granted. However, this not only has this property, this choice tells you that you have n times n minus 1 over 2 vectors at the massless level, and the same number of spinors. So the theory has an adjoint multiplet of spinors that accompany the vectors. So it's the Young-Mills theory in 10 dimensions. For what gauge group? For gauge group SO32. So we have rediscovered the type 1 superstring in a systematic way. Now, if you didn't discover any other theory, then it would not be useful. But all theories in lower dimensions follow from the same kind of situations. You can build all string theories which have an open sector by the same technique. In the couple of minutes that are left, I want to raise a question that we will answer next time. And the question, I will raise it with reference to this theory. You see, instead of having only two diagonal sectors, here the diagonal sectors are V8 absolute value squared and S8 absolute value squared. This is the richest theory in this respect. It's a tachyonic theory, but nonetheless, it has four diagonal sectors. And the question I want to raise with you is what kind of Klein-Bottle projections are consistent for this theory? Well, if the theory is this 0b, what kind of Klein-Bottle projections can you write down? Well, first of all, I will write the natural Klein-Bottle projection. Well, symmetrizing the Navier-Schwartz sectors and anti-symmetrizing the Ramond-Ramond sectors. What kind of K tilde do you get here? I tell you that if you do this, O plus V minus S minus C will give you a K tilde which will involve V8. Fine, V8 exists. Because it's V8, V8 bar, it can bounce at on the boundaries at the end. It's a consistent choice. How about if I want to be more exotic, like I was trying to do before? I try to do this Klein-Bottle projection with all plus signs. Fine, I can do it again, because if I do a modular transformation, I get that K tilde now involves O8. No problem, O8 exists there, perfectly consistent to let it bounce along two crosscuts. There's no violation or anything. But let me try to do something more interesting. How about if I do this? Minus O8 plus V8, say minus S8 plus C8. Why is this interesting? Can you tell me why this choice is special and very interesting? Any one of you has any clue? Do you? Count the number of tachyons. How many tachyons do you get? I told you that each sector starts from the particle that you are. So here, once you put tau goes to tau over 2, here you get half a tachyon. And here you get another half of a tachyon, so you get one tachyon together. How about here? Half minus half is 0. So it means that you have a projection of a theory which a priori would be tachyonic, but due to the Klein-Bottle projection, you get a closed string spectrum which is free of tachyons. And now, the question, is this consistent? Yes, it is. Because if you try to do this transformation, then the stuff that you get in the right channel, in the transverse channel, is S8. S8 is fine because S8 is S8 bar. I mean, you use that S matrix that I gave you, and you get this answer. Why are these conditions consistent with interactions? And the point is that if you anti-symmetrize two states, rather than if you change the symmetry property of certain states with respect to this standard choice, it must be consistent with the interactions. And next time we'll see that it is. So this theory is a theory where the closed part contains no tachyons. And it's possible also to get an open part with no tachyons. And this will be one of the three non-supersymmetric 10-dimensional string models. Two of them are orientifolds, and one of them comes from the diatoric string. So studying the one that comes from the diatoric string will give me a chance to repeat some of the ideas that I gave you about the diatoric string, which were indeed a little bit dense.